Good morning, students. Now I am going to discuss about the first law of thermodynamics and the applications of first law of thermodynamics. Any thermodynamic system in an equilibrium state possesses a state variable called internal energy. Between any two equilibrium states, the change in internal energy U is equal to the difference between the heat transferred into the system and the work done by the system. Okay, so between any two equilibrium state, the change in internal energy is equal to the difference between the heat transferred into the system and work done by the system. Internal energy is nothing but the total energy of the system when the system is not exerted by the external force. Okay, so this is mathematically expressed as U2 minus U1. So this is between any two equilibrium state, the change in internal energy is equal to the difference between the heat Q transferred into the system and the work done by the system. That is, upon rearranging this equation, we can write Q is equal to W plus U2 minus U1. This is the mathematical formulation of first law of thermodynamics. For an infinitesimal process, the above equation can be expressed as, so what is the meaning of infinitesimal? That is a very small change in the process. Then the above equation can be expressed as dq is equal to dw plus du, but dw is equal to p into dv. So we can write dq is equal to du plus p dv, where dq and dw are not exact differentials, but du is the exact differential because u is the state function of the system. Okay, so state function is nothing but it represents the states in a system. So dq and dw are not exact differentials, but du is the exact differential, and a detailed study of exact differential will be studied in thermodynamic potentials. Okay, so dw is the exact differential because u is the state function of the system. This is the first law of thermodynamics. So first law of thermodynamics, the equation is, general equation is dq is equal to dw plus du, and dw is equal to p dv. Therefore we write dq is equal to du plus p dv. Now work done in an isothermal process for an ideal gas. What is an isothermal process? It is the process that takes place at constant temperature. Now consider an isothermal expansion of an ideal gas whose pressure and volume changes from P1 V1 to P2 V2. During a quasi-static process, the work done by the system is given by W is equal to integral V1 to V2 P into dV. What do you mean by quasi-static process? It is a slow changing process which continue to keep the system in internal thermodynamic equilibrium. Okay, so during a quasi-static process, the work done is given by W is equal to integral V1 to V2 P dV. The equation of state of an ideal gas is given by PV is equal to nRT. From this equation, P is equal to nRT by V. Now you substitute equation 3 in equation 1. That is, in the place of P you substitute nRT by V. Therefore W is equal to integral V1 to V2 nRT by V into dV. nRT is constant, take it out, so integral V1 to V2 dV by V. So integral of dV by V is nothing but ln of V2 by V1. Therefore we got W is equal to nRT ln V2 by V1. Since for an isothermal process P1 V1 is equal to P2 V2, by cross multiplication we can write V2 by V1 is equal to P1 to P2. So in the place of V1 divided by V2 we can write P1 by P2. Therefore W is equal to nRT ln P1 by P2. Okay, and equation 4 and 5 can also be written as W is equal to 2.303 nRT log to the base 10 P1 by P2, that is also equal to 2.303 nRT log to the base 10 V2 by V1. That is, we are writing equation 4 and 5 in terms of log to the base 10. This is the work done in an isothermal process for an ideal gas. Next is internal energy as a state function. What is the internal energy? Internal energy is nothing but the total energy of the system when the system is not subjected to any external force. So internal energy is a function of two coordinates out of the three coordinates describing the equilibrium state of a closed hydrostatic system. What are the three coordinates? They are nothing but pressure, volume and temperature. Okay, so internal energy is a function of two coordinates out of the three coordinates, pressure, volume and temperature, describing the equilibrium state of a closed hydrostatic system. What do you mean by hydrostatic system? That is the liquid which is at rest. Okay, that is the force exerted by the liquid when it is at rest. That is a hydrostatic system. Now, internal energy is a state function, hence the infinitesimal change of internal energy du is an exact differential. Okay, it is an exact differential because it is a state function. The integral of du is independent of the path between the initial and final states. For example, if P1 V1 is the initial state and P2 V2 is the initial state, is the final state, then the integral of du is independent of the path between the initial and the final states. Internal energy of a hydrostatic system can be a function of T and V, that is U of T and V. Then du, since it is an exact differential, I can express du in terms of dou U by dou T at V into dt plus dou U by dou V at T into dV. That is, you have two coordinates T and V. So the partial differentiation of U with respect to T, that is the first coordinate, at the constant of second coordinate into dt plus the partial derivatives of dou U with respect to the second coordinate at the constant of first coordinate into dV. So expressing in this form is called as exact differential. du we can express in terms of exact differential. Okay, so as I said in the first part, dq and dw are not exact differentials because dq and dw we cannot express in terms of those partial derivatives. but du is an exact differential because it is a state function. That's why we have expressed in this as du is equal to dou u by dou t at v into dt plus dou u by dou v at t into dv. Now, if we express internal energy of a hydrostatic system as a function of temperature and pressure, we can write u of t comma p, then du is equal to dou u by dou t at p into dt plus dou u by dou p at t into dp. Internal energy is a perfect differential of the thermodynamic variables. Okay, perfect differential is nothing but exact differential. Hence, it is a state variable. So, this is all about internal energy as a state function. Next comes application of the first law of thermodynamics. The first application is cyclic process. The process in which the initial and the final state is the same is known as the cyclic process. Okay, so as the name cyclic, it implies the initial and the final state of the system is the same. It is a sequence of processes that leave the system in the same state in which it started. Okay, that is, even after certain processes, the system will come back to its initial state. Fine, that is what is written here. It is a sequence of processes that leaves the system in the same state in which it was started. When a system undergoes a cyclic process, its initial and final internal energies are equal. That is, U1 is equal to U2. Fine. Hence, the internal energy change in any cyclic process is 0. Okay, since initial and final internal energies are equal, any internal energy change in the cyclic process is 0. Applying the first law of thermodynamics to a cyclic process, we get dq is equal to du plus dw. This is the first law of thermodynamics. In cyclic process, internal energy is 0, therefore du is equal to 0. This implies dq is equal to dw. Hence, the work done by the system in a cyclic process is equal to the heat absorbed by the system. Okay, the work done, as this equation implies, the work done in a cyclic process is equal to the heat absorbed. Q is nothing but heat absorbed by the system. The network involved in a cyclic process is the area enclosed in a PV diagram. I can show the diagram. This is the PV diagram. So this is the network enclosed by the PV diagram. So initial and final states are equal in a cyclic process. If the cycle goes clockwise, work is done by the system, and if the cycle goes anti-clockwise, then the work is done on the system. So for clockwise, work is done by the system, and for anti-clockwise, work is done on the system. An example of such a cyclic system is a refrigerator or air conditioner. Second application is adiabatic process. The process in which heat in a system remains constant but pressure and volume changes is called adiabatic process. Okay, heat remains constant. That is, no heat enter the system or leave the system. In turn, heat remains constant in a system, but pressure and volume can change. That is called adiabatic process. In thermodynamics, An adiabatic process is one that occurs without transfer of heat or matter between a thermodynamic system and its surroundings. Okay, that is, no heat enters or leaves the system. In an adiabatic process, energy is transferred to its surroundings only as work, not as heat. Okay, only energy is transferred to its surroundings as work. And in an adiabatic process, heat is not exchanged. So in case of adiabatic expansion of gas, dq is equal to 0. Okay, because dq is constant. The first law of thermodynamics, we know it is dq is equal to dw plus du. Since dq is equal to 0, we get du is equal to minus dw. That is, if the initial internal energy of the gas is U1 and the final internal energy of the gas is U2, then equation 1, okay, this is equation 1, can be written as, instead of du we can write U2 minus U1 is equal to minus dw. This implies U2 is greater than U1. See, it is minus dw. Only if, U2 is less than U1. Only if U2 is less than U1, you will get minus dw. Okay. So, this means during adiabatic expansion, internal energy of the system decreases due to external work done. So there is a minus sign. du is equal to minus dw. So internal energy of the system decreases due to external work done. Consequently, temperature also decreases. So this is in the case of adiabatic expansion. The opposite happens in adiabatic contraction. Okay. So similarly, in the case of adiabatic contraction, dq is equal to 0. But in the case of adiabatic contraction, work is done on the system. Okay, work is done on the system, therefore dw is negative. Whereas in adiabatic expansion, work is done by the system. Fine. So here dw is negative, therefore equation 2, from equation 2 we get du is equal to u2 minus u1 is equal to minus of minus w, minus dw. That is, dw is negative in the case of adiabatic contraction. Fine. So we get du is equal to plus dw. So this can happen only if u2 is greater than u1. Whereas in adiabatic expansion, u2 is less than u1. But here u2 is greater than u1. This means during adiabatic contraction, internal energy of the gas increases. So the temperature of the gas also increases. Okay. Internal energy of the gas or the system increases. So the temperature of the system also increases. Now, relation between P and V in the case of adiabatic process. According to first law of thermodynamics, we know it is dq is equal to du plus dw. For 1 mole of a gas, du is equal to Cv dt, where Cv is the specific heat capacity for 1 mole of a gas at constant volume. And we know dw is equal to P into dV. Now substitute in this equation the first law of thermodynamics. We get, and for the adiabatic process, dq is equal to 0. So this is the first law of thermodynamics, dq is equal to du plus dw. Substitute those values. So 0 is equal to Cv dt plus P into dV. According to ideal gas equation, PV is equal to RT. Now you differentiate both the sides, we get P into dV plus V into dP is equal to R into dt. R is a molar gas constant. So from this, what is dt? dt is equal to P dV plus V dP divided by R. Now you substitute this dt is equal to P dV plus V dP by R in this equation. Okay, in this equation, that is 0 is equal to Cv dt plus P dV. So we get Cv into, in the place of dt, I write P dV plus V dP divided by R plus P into dV is equal to 0. Now you multiply inside and take LCM. So you get Cv P dV plus Cv V dP plus Rp into dV equal to 0. Okay. Take LCM and multiply with the Cv. Okay, this term, the first term in the LHS, you multiply with Cv and you take LCM, you will get this. Now group the dV terms. So here CVP dV and RP dV. Group this, so you will get CV plus R into P dV. Fine. So P dV is common in the first and the third term. Take it out, you will get CV plus R. And the second term remain the same. CVV dP plus CV plus R into P dV is equal to 0. So CVV dP plus CV plus R is equal to Cp. This is Mayer's relation. So instead of Cv plus R, you substitute Cp, where Cp is the specific heat capacity of 1 mole of a gas at constant pressure. So Cp into P dV equal to 0. Now dividing both the sides by Cv PV. Okay. So we get CVV dP by CV PV plus CP PdV by CV PV equal to 0. Now you cancel the like terms. CVV will get cancelled in the first term. So the remaining is dP by P plus, here in the second term P and P will get cancelled. The remaining is Cp dV divided by Cpv equal to 0. So finally it is dP by P plus Cp by Cv is nothing but gamma. Gamma is nothing but the atomicity of gas. Okay, Cp by Cv. So gamma into dV by V equal to 0. Now upon integrating, we get integral dP by P plus gamma into integral dV by V equal to a constant. So after integrating, we get log to the base E P plus gamma log to the base E V equal to constant C. So where gamma is the atomicity of the gas and gamma is equal to Cp by Cv. And applying the logarithmic rules, okay, we can write this log to the base EP plus gamma log to the base EV equal to constant. We can write it as, apply the product rule and the addition rule. So we can write log to the base E PV gamma equal to C, which is a constant. So in turn we can write PV gamma, PV power gamma is equal to exponential power C. So this implies this exponential power constant is again a constant. So we can equate it to another constant k. So PV power gamma is equal to constant k. Now this equation gives the relation between pressure and volume of an ideal gas. So what is our heading? It is the relation between pressure and volume of an ideal gas in the case of adiabatic process. Similarly, we can find out the relation between pressure and temperature in an adiabatic process. So we know that PV is equal to RT, that is ideal gas equation for 1 mole of a gas. Okay, so N is equal to 1. Usually we write PV is equal to nRT. So for 1 mole of a gas, N is equal to 1. So we have written PV is equal to RT. This implies V is equal to RT by P. Substituting the value of V in the above equation, that is in the first relation, okay, PV gamma is equal to K. That is the relation between P and V in an adiabatic process. So PV gamma is equal to K. Substitute V is equal to RT by P. So P into RT by P the whole power gamma is equal to K. Fine. So this we can write as P is in the numerator and there is another P in the denominator with the power minus gamma, right? So the power gamma, so once it comes to the numerator, I can write P power minus gamma. So P power 1 minus gamma and T power gamma is equal to K divided by, see K is a constant. What is R? R is again a constant, molar gas constant. So I brought R towards the other side. So K by R power gamma, that is equal to constant. So in turn I can write P power 1 minus gamma T power gamma is equal to constant. Okay. Next is relation between V and T. So the above equation gives the relation between P and T in the case of adiabatic process. Now relation between V and T in a adiabatic process. Again we know that PV is equal to RT for 1 mole of a gas. This implies PV is equal to RT by V. Substitute the value of P in the first equation. Okay, first relation, that is PV gamma is equal to K. So instead of P you substitute RT by V. So RT by V into V power gamma is equal to K. And bring this R towards the other side and T, V is in the denominator. So it becomes, when it comes to the numerator, it becomes minus 1. So I can write TV power gamma minus 1 is equal to K by R. K by R is again a constant. So TV power gamma minus 1 is equal to constant. This equation gives the relation between volume and temperature. Okay, so these are the 3 relations. Summary: the adiabatic relation between P and V is given by PV power gamma is equal to constant. The adiabatic relation between P and T is given by P power 1 minus gamma, T power gamma is equal to constant. The adiabatic relation between V and T is given by T V power gamma minus 1 is equal to constant. So we saw cyclic process, adiabatic process. Now the third one is isochoric process. Okay, that is application of first law of thermodynamics in isochoric process. So an isochoric process is a thermodynamic process in which volume remains constant. That is, work done by the system will be zero. Okay, work done by the system will be zero in the case of isochoric process. Therefore, from the first law of thermodynamics, we have dq is equal to dw plus du. Since the work done is zero, dw is equal to 0. Therefore, we get dq is equal to du. But at constant volume, dq is equal to Cv dt, where Cv is the specific heat capacity for 1 mole of a gas at constant volume. Therefore, equation 4 implies instead of dq, write Cv dt. Cv dt is equal to du. Okay, this is equation 5. Next is isobaric process. So an isobaric process occurs at constant pressure. Since the pressure is constant, the force exerted is also constant, and the work done is given by P into dV. Once again, from the first law of thermodynamics, dq is equal to dw plus du. Since the work done is given by P into dV, instead of dw, substitute P into dV. So dq is equal to P dV plus du. But at constant pressure, dq is equal to Cp dt. Okay. In the case of isochoric process, where volume is constant, dq is equal to Cv dt, but here it is Cp dt. So substitute in equation 6, we get Cp dt is equal to P dV plus du. From equation 5, okay, from equation, this is 5, equation 5, du is equal to Cv dt. So you can substitute now in equation 7, instead of du, substitute Cv dt. So we get equation 7 becomes Cp dt is equal to P dV plus Cv dt. Ideal gas equation is PV is equal to RT for 1 mole of a gas. But for an ideal gas, work done at constant pressure is P into dV is equal to R into dt. Okay. Work done at constant pressure is P into dV is equal to R into dt. So in equation 8 we have P into dV. So instead of P into dV, substitute R into dt. So you will get like this, that is Cp dt is equal to R dt plus Cv dt. Now dt is common both the sides, so you can divide by dt throughout. You will get Cp is equal to R plus Cv. This relation is called Mayer's relation, that is Cp is equal to R plus Cv. Okay. Next is isothermal process. What is an isothermal process? That is a process in which temperature remains constant. Since temperature remains constant in an isothermal process, du is equal to 0, because internal energy is directly related to the temperature. So since temperature is constant, du is equal to 0. Once again, from the first law of thermodynamics, dq is equal to du plus dw. Therefore, since du is equal to 0, dq is equal to dw, which is equal to P into dV. Thus, for an ideal gas, if the temperature is constant, internal energy is also constant. These are all about the first law of thermodynamics and the applications of first law of thermodynamics. Hope you all understood. Thank you.